Hello. In this video, I'd like to go through with you a brief introduction to derivatives in the world of calculus. Calculus is the language of change, And we seek to describe how fast things are changing, because that's fundamentally how we measure change, right? If you're earning $1 an hour, that's different fundamentally from if you're earning $10 an hour, or if you're adding a gallon a minute to your pot of water. That's really different than if you're adding 10 gallons a minute to your pot of water, or subtracting a gallon of water per minute from your pot of water. Okay? So in the world of calculus, we're going to measure change. Okay? So calculus is all about the language of change. And what we're going to do is we're going to work in terms of functions. And there's a whole world of calculus that deals with noisy data and data from sensors and stuff like that. But we're going to take our data from functions. So we're going to deal with functions f. So f is going to be a function. And we want to measure how fast f is changing. So f is a function that quantifies state, quantifies how much water is in my pot of water. How far have I gone? Okay. So we have functions because they're nice to work with, mathematically speaking, and we're going to think about them modeling how much water, how far have I gone, things like that. And basically any state you can think of and represent numerically as having some numerical value, we're going to be able to model using functions f. And we want to ask the big question in the world of derivatives. How fast is f? How fast is f changing? That is the primary question that derivatives answer. And that's half of the picture for calculus, which is the language of change. So we're going to represent that with notation as df dt, or perhaps df dx, or whatever your variable happens to be. We like to use t for time. We like to use x for space. Maybe your function isn't called f because f is just f for function. Maybe it's called p for pressure. Maybe it's called s for state. Maybe it's called w for water. It doesn't really matter. So we're going to measure how fast f is changing, and we're going to represent that with a symbol, df dt, df dx, or whatever it happens to be. We'll come back later and talk about why we represent it as this fraction right here. But for now, my point was that I want to say calculus is the language of change. We're going to do derivatives, and I want to bring out my trusty medical device that explains derivatives. Okay, so f is going to be my air in my lungs. Okay? So I'm going to have 0 air in my lungs when the bar is down here. And as I inhale, I'm inhaling because this thing measures how much air is in my lungs. I'm going to inhale. You ready? And it's pretty clear that the amount of air in my lungs varies over time. So we're going to say 0 is right there. And it peaks out at 400 milliliters or 4 liters at the top of this device. So this device isn't capable of measuring more than that. And I want you to pay attention to this thing right here. df dt, because the state is varying with respect to time. I'm in control of this. I'm controlling this, and then that induces change on this. This measures how fast the amount of air in my lungs is changing. Check this out. Let's see here. I think you should be able to see the bar in my little window I drew here. Okay, I'm going to do that one more time. I'm going to do that one more time after I erase these bars right here, in case you can't see because I drew the bar. So we're watching this marker inside this chamber right here. And I want you to notice that the faster I inhale, the more I inhale, the higher this goes, and the faster this thing changes. Okay? So the faster this is changing, the higher this bar is. Barely inhaling, bar doesn't go very high. This thing creeps up. Breathing in pretty hard. The bar right here goes higher. This thing rises faster. Okay? So this device right here demonstrates the concept of derivatives. And the bar right here is the derivative of this thing. So the height of this bar, and I'm just going to write this down to be explicit with it. The height of the marker in here is df dt. The height of the marker is the derivative of the amount of air in my lungs given on the left-hand side. So as we move forward right here, we're going to want to explain why we use this ratio right here. And then given an F, how do I compute df dt, df dx? And that's coming up. That's not for right now. So thank you so much for watching, and I will catch you later. Bye.